Okay, so I want to start off with this idea of talking about a tangent line. We're going to do this thing called linear approximations, okay? So here's what we know about a tangent line so far. We know that if I have this curve, I'm going to be able to attach a tangent line at one point. Now, what's kind of interesting about a tangent line is that a tangent line does more than tell you the slope at that point. It also gives us a useful way to approximate a value on the curve. Now, normally, everything we've done up to this point, we've written our tangent lines as y minus y1 equals m, x minus x1. And I could technically, if I wanted to even be more specific, if I have a particular x and a particular a, I might be able to say it's y minus, instead of y1, we'll use the term f of a, equals, instead of slope, I'm going to say f prime of a, x minus a. So really, this is not anything new. Instead of using this idea of a point being x and y, I'm now saying that this point is a and f of a. And instead of using the letter m for slope, I'm just saying f prime of a. So what we're going to do today is use a tangent line to find an approximation of a value on the curve. Now, what I want to do is arrange my terms. If I take this equation right here and solve it for y, I could also say that this is equal to y equals f of a plus f prime of a times x minus a. So in this case, our y-coordinate, our y represents the y-coordinate of a on our tangent line. And this gives us an approximation of f of a. And our y-coordinate of a of the function is represented by f of a. And f of a is the actual value. Now, all of this jargon sounds really, really good until you understand what it is we're about to do here, okay? What we're going to do is say we have this curve, okay? And I have this tangent line at this point right here, okay? What we're going to do is use our tangent line to estimate a value on our graph that's just a little bit off. And if you see it, if I take the point on the tangent line and the point on my curve, they're going to be pretty close. And the closer I can get to whatever this value is where the tangent line was created, the closer it's going to be. Now, this sounds really difficult, but this is an easy topic. Okay? So here's what we've got. I've got a function y equals x squared. Step number one, I want to write the equation of a tangent line. You've been doing this since like the third week of calculus. So if I want to write the equation of a tangent line, the first thing you need is you need a point and you need a slope. Okay? So I know that f of x is x squared. So f prime of x is going to be 2x. If I evaluate this at x equals 1, then f prime of 1 is 2, and f of 1 is 1. Put all this together into my tangent line. I have y minus 1. My slope is 2. X minus 1, okay? Now what we're going to do is instead of write the tangent line like this, I'm going to take this 1 and I'm going to add it to the other side to make this y equals 1 plus 2x minus 1. This is now going to be my tangent line approximation. I'm going to use this tangent line to approximate a value. Part B says, I want to use my answer from part A to find an approximation for f of 1.1. So what this means is, instead of plugging 1.01 into my function, I can use my tangent line, y equals 1 plus 2x minus 1, to approximate f of 1.01 by plugging in 1.01 in for x, and I'm going to get approximately 1.02. Okay? So part C says, hey, go find the actual value of f of 1.01. So keep in mind, f of 1.01 is talking about my original function f of x. So I'm just going to say 1.01 squared. If I put 1.01 squared in the calculator, I'm going to get 1.0201. So you'll notice that these two values right here are pretty darn close, and they should be, because what I've just done is used my x squared graph, and I've said, hey, here at this point 1, where I've got a tangent line, I'm going to use this tangent line to get a really, really close value right next to it. And I used my tangent line to approximate it. Okay? So then there's this concept of error. How close are these 2 points? How close are these 2 points? Well, we want to think about error as the distance between them. In other words, the absolute value of the distance between them. So if I take the absolute value of the difference, I should get that my error is 0.0001, which is pretty small. Okay? So the other thing I can do with these tangent line approximations is use them to actually find values that I can't do in the calculator. Okay, now this is going to seem like a really, really weird concept because you have a calculator while you're doing this. So let's read this next question. It says, I want to use the tangent line approximation to approximate the value of the cube root of 127. Okay, now that's all you're going to get if you see something like this on the exam. But to do this, you have to understand, if I want to find the cube root of 127, I'm really asking you to consider the function cube root of x. So let's lay down some background information. Okay? First off, I'm going to let my function be the cube root of x, which is going to mean that my derivative is 1/3 x to the negative 2/3 power. Okay? The next thing I'm going to need is I need to know what I'm actually going to use as my x values. Okay? So keep in mind, if we're talking about the cube root of x, and I want to estimate the cube root of 127, I need to figure out a number that's pretty close to this. So we're going to use x equals 125 to estimate the cube root of 127. Okay? Well, you're probably wondering, why did I pick 125? I picked 125 because it's a perfect cube. So now I need to find f of 125, and I need to find f prime of 125 because we're going to use those in our tangent line. Okay? F of 125, well, the cube root of 125 is 5. Okay? And 1/3 times 125 to the negative 2/3 power should give me 1/75. So now what I want to do with all of this is turn this into my tangent line. Okay? So y minus y1, well, y1 is 5, equals my slope, x minus x1. Well, what's my x value I'm using? I'm using 125. So I now have my tangent line, but remember, we don't want to write it like that. We want to write it so that it's solved for y. So this is 5 plus 1/75 x minus 125. And I'm going to use this to answer my question. I'm going to use this to answer my question. I want to know, what is the cube root of 127? So 127 is pretty close to 125, so I'm going to plug in 127 in for x. And when I do that, I find that my y value is approximately 5.026 repeated, okay? Well, how close would this have actually been to my actual value? How close would this have been to my actual value? So let's see. What is the cube root of 127? If I put that in my calculator, I should get about 5.027. So we're pretty darn close. In fact, if you were to type in the difference, my error ends up being within 0.0000141. If you check that out, okay? So pretty darn close. So our tangent line approximation got us really, really close to the actual value of the cube root of 127, okay? So I'm now going to switch gears completely and talk about this idea of a differential. Now, this is really kind of diving back into history a little bit, and you might be thinking while we're doing this, what in the world, what are you doing? So I just want you to kind of hold the phone and see how this kind of unfolds. So there's a guy named Leibniz. Leibniz is probably one of the major fathers of calculus. And one of the things you'll notice is that there's lots of notations that we use for the derivative, and one of those notations that we use is called dy dx. We use y prime, we use f prime. Those all stand for derivative. In fact, it stands for the derivative of y with respect to x. Okay? Now this notation, interestingly enough, looks like a quotient of division. But what I want you to understand is when they actually came up with this stuff, it is really a limit in which the quotients, limit of quotients in which the numerator and the denominator both go to 0. Because remember, delta y and delta x is the change in y over the change in x. We're talking about making the change in y infinitesimally close and the change in x infinitesimally close. So when Leibniz was doing calculus way a long time ago, he said he actually never used dy dx. He did all of his calculus using dy dx as separate entities, but he never quite figured out what they were. And so what he called them is he called them infinitesimals, non-zero numbers that were infinitesimally small. Now, I want you to understand that it is not typical for us to treat dy dx as separate entities. And we're really not going to be doing this a whole lot. This is such a small topic in BC calculus. So if we could separate them, dy and dx, as formal variables, this is how we would do that. We're going to let y be a differentiable function, y equals f of x. We're going to call dx an independent variable. And we're going to say that dy is equal to f prime of x dx. Now, what does this look like? This kind of looks like the derivative of x dx, almost kind of like chain rule, okay? Now, in this case, dy is always the dependent variable. It depends on both x and dx. So we're going to like algebra this. Here is y equals 5x cubed, okay? If I took the derivative of y with respect 2x, I could say this is equal to 15x squared. Well, what if for a second I could take my dx and multiply it to the other side? Then I could say that dy is equal to 15x squared dx. Now this is not a typical thing, and this is really not applicable and useful in the scope of what we just did a second ago. But where it is applicable and useful is in a question like this. The radius of a circle increases from 10 to 10.1. Use the differential dA to estimate the increase in the circle's area. Okay, first thing, how do you find area of a circle? Pi r squared. I'm now going to take the derivative of area with respect to r. If I take the derivative of area, I get 2 pi r, okay? What if I multiply my dr to the other side? I can now say that dA is equal to 2 pi r multiplied by dr. Okay, so this is a formula that represents the differential dA. Now, I can use this as an estimate for the increase in area, because dA literally means change in area. So I'm going to say 2 pi. What was the original radius? 10. dr represents the change in my radius. How much did it change by? To go from 10 to 10.1, dr is 0.1. If I multiply this out, I'm going to find that this is equal to 6.283 meters squared. Okay, I want to compare this estimate with what I found. This estimate in A with a true change. So true change, we're going to do this the algebra 1 way. My original area, pi r squared, no derivative about it. If I plug in pi, a radius of 10, and I square it, I get 100 pi. If I plug in, and I'm going to use a subscript, a is sub 10. If I plug in 10.1, my new radius, I should get 102.01 pi. So what is the difference? How much did this change by? So to find how much it changed by, I can say 102.01 pi minus 100 pi, and I'm going to get an exact decimal. You should get 2.01 times pi, which is approximately 6.3146 meters squared. Well, interestingly enough, these aren't exact, but they're pretty darn close. And that's what Leibniz discovered. He discovered that I could find changes in area, changes in volume using this idea of a differential, okay? Now, it's not exact, but it sure works as an estimate. Let's do another. Suppose the Earth were a perfect sphere, and we determined its radius to be 359 plus or minus 0.1 miles. What effect would the tolerance of 0.1 miles have on our estimate of the Earth's surface area? Let's start with that. So starting with surface area of a sphere is 4 pi r squared. If I take the derivative of surface area with respect to r, I'm going to get 8 pi r. I'm going to multiply my dr to the other side to give me the derivative of surface area is equal to 8 pi r dr. Okay? So filling this in, what is my original radius of the Earth? We said it was 39.59. What is dr? Well, our dr is going to be represented by this plus or minus 0.1, so we'll call that 0.1. And if we do that, I'm going to find that this is 9,950.052 miles squared. And I'm going to put a plus or minus in it because that means that if this is a plus or minus 0.1 miles, technically my surface area could be off by as much as close to 10,000 miles. Okay? I'm going to do the same thing with my volume. Volume of a sphere is 4/3 pi r cubed. I'm going to take the derivative of volume with respect to r. I'm going to get 4/3 times 3 pi r squared. My 3's will cancel, and I'm going to multiply my dr to the other side. So I get dv is equal to 4 pi r squared times dr. Let's fill it in. dv is equal to 4 pi. My radius of the Earth is, oh, I already messed it up. Sorry, guys. My radius of the Earth is 39.59. My plus or minus threshold is 0.1, plus or minus 0.1. And if I plug that in, and I forgot to square my radius, if I plug that in, I'm going to find that the volume of the Earth could vary by as much as 19,696.43. Sorry about that. And the units on that would be miles cubed. Okay? So what's really cool about this is using this idea of a differential kind of gives us a way of finding the change in something by simply multiplying that dr to the other side. Or in the previous example, r, I think it was an r as well, but multiplying it over to the other side. And we're not going to use this very often. Please don't think that this is a really, really common application of the derivative.